Hello, Physics 1 students. In this video, I'm going to derive Newton's second law for rotations. And I'm talking about rotations of rigid bodies, so everything has to be a rigid shape. So the idea in my mind is kind of from the top, the bird's eye view of things. I've got some sort of a shape, and there's some sort of an axis of rotation, that in green. Got some sort of an axis of rotation, and I'm going to imagine that the shape is going to rotate with some angular velocity, possibly some angular acceleration, about this point. We're going to imagine that there are various forces being applied. So, well, various torques being applied. So you can imagine various strings and things. You could have a force applied here and some other force applied here, all sorts of things you could imagine acting on this, causing it to want to rotate. Now, you could have, say, force 1 and force 2. For real objects, they can simultaneously move, their centers can move, and they can rotate as they move. Right now, I want to focus on the rotation part. So with that caveat that we're just focusing on the rotational part of the motion, let's see what we can do. As always, when we have these sorts of extended shapes, we sort of break it up into little pieces. So I'm going to do that. I'm going to kind of think about a portion here. I'll just pick out a little chunk of it, and I'll label this piece with a label I. And you can imagine there are many such chunks, and as you add them all up, you get the whole shape. So what we've already defined the definition of torque. Remember, torque due to a force would be R cross F. And what I want to do here is I want to focus on the net torque. So I'm going to define the net torque on this little chunk of mass. So I'll label net torque on this. It's simply going to be the position of this little chunk relative to the pivot point, the axis of rotation, cross F. And here I'm talking about the net force. So just to draw it out, this would be Ri. Now, oh, there should be a comma there, I suppose, so you keep it clear. This is the net force on the ith particle. Note, on this little chunk, I didn't draw any external forces, but you could imagine there are both internal forces, neighboring pieces of mass pushing on it, and external forces, external strings and things attached to it. So F net on the ith mass has both internal and external forces. All right. But it's important to remember that with the internal forces, well, we'll see what happens. Something happened. They end up dropping out, not being important. So we'll work that out. The other thing is, since we're rotating about this point here, what we learn is that, well, if you think about it, F net for mass I is simply going to be the mass of I times the acceleration of particle I. But because this is undergoing circular motion about this axis, I can write AI as a radial component, so that's going to be the centripetal acceleration, that's going to be minus, we can write it as vi squared over ri times ri hat, right? Because it would point towards the center of the circular path, so it's going to be minus r hat. But this is the usual centripetal acceleration, v squared over r. And then you would also have the tangential component of acceleration. So you do say plus a tangent for the ith mass, and that would point in the theta hat direction. So the general acceleration for this particle moving in a circle would be both a mixture of centripetal and tangential. So I'm going to plug this into here, and then we'll go up here and take the cross product and see what falls out. So I'm going to have that the net torque on the ith particle, so the net torque on the ith particle is given by the formula Ri cross the net force, well, that'd be Mi times Vi squared. I suppose there's a minus sign over Ri minus R hat I. Remember, hat means unit vector, has length 1. It just picks out the direction. This is the radial part of the acceleration, so it's centripetal acceleration, plus I would have a tangent for particle I, and it would be in point in the theta hat direction. And I need to multiply by the mass of the ith particle. This factor of mass fact goes through. Now, Ri is parallel to Ri hat, and parallel vectors have no cross product. So this one gives 0, doesn't matter. I'm left with Mi times Ri vector cross a tangent I times theta hat. Because Ri equals Ri scalar times R hat I, and R hat cross theta hat equals Z hat, I can write this out simply as Mi Ri squared times alpha, where I'm using the fact that a tangent equals R alpha. And this would all be in the Z direction. Whew, it's a bit of a mess. You have to combine lots of little things that we've been learning about through the semester. But this final answer is going to be very simple. So even if you don't follow the logic of how that went, the final result is simple enough that you'll be okay. All right. That's for one piece of mass. What I want to do, or have some shape, is I want to add up the effects of all the pieces of mass. So I want to find the net torque for the whole object. That's simply going to be the sum of this. And I also note that alpha and z hat are independent of the label, and therefore I can just pull them out. Very good. I think you'll start to see what happens here. So rewriting this, I find that the net torque on the whole object equals, passing to the limit, integral dm of r, going to be the perpendicular distances ri squared times alpha z hat, that's nothing than an alpha vector, and this is the moment of inertia. So we get that the net torque equals, on the whole object, equals I times alpha. Some comments. When passing from the net torque on one element to the net torque on the whole object, all of the internal forces push against each other and they actually cancel out. So we now only include external forces. You don't have to worry about the amount that one drop puts on another drop. You just worry about the external forces that act on the whole object. The other comparison I want to make is, when we talked about kinetic energy for translational and kinetic energy rotational, we found that there was a sort of a dictionary relating velocity and omega. And on the translational side, we had mass. And on the rotational side, we had moment of inertia. And now we can enlarge that dictionary. On one side, we have Newton's second law, which says F equals ma. That becomes, for rotational problems, torque equals I times alpha. And we see there's a dictionary then, we can enlarge the dictionary to include forces being analogous to torques as far as rotational motions are concerned. And acceleration is analogous to angular acceleration, which is perhaps not too surprising if velocities are going to be analogous to angular velocities. So in fact, for many, many, many problems, if you can just remember how to apply F equals ma and change the spelling from Latin letters to Greek letters for rotational problems, you will end up in the right place. Another comment, remember I said that when we have rotations in a plane, rather than worry about the full, we won't worry about the full 3D vector part of the torque. We will just say torques are positive or negative. So don't worry about the z direction stuff. Just worry about clockwise or counterclockwise in the usual sense. There's one thing I forgot to mention last time before I go here. And that is units. What are the units of torque? Well, that's going to be a Newton times a meter. And you might say, we've seen that before, and you'd be right. This is the same as a joule. A Newton meter is a joule. But for torque problems, we always talk about it, we just leave it as Newton meters. Or people talk about foot-pounds of torque when you tighten bolts on a tire, things like that. I think it's just a convenient way to remember the difference between torque and energy. They have the same units, but torque is a vector quantity, whereas energy is a scalar quantity. So by treating their units differently, it's just a verbal way of reinforcing the distinction between them. Okay, so I'm going to stop here, and in the next video, I'm going to apply this law to solve some problems. All right, thank you.